Now we are going to another important theorem. Let H be a Hilbert space. A is in VLH. Then a range of A equals H if and only if A star is bounded below, and range of A star equals H if and only if A is bounded below. We know what is A is bounded below. A is bounded below means, what is the bounded below? A is bounded below. A is bounded below means some beta norm x, there exists some beta greater than 0 such that beta norm x less than or equals to norm x. Beta norm x less than or equals to norm x for all x fall in H. So this is the condition for below bounded of A. A is bounded below means there exists some beta greater than 0 such that beta norm x less than or equals to norm x for all x fall in H. Now, here first assume, first equation, assume Ra is H, range of A equals H. A from H to H, what is A? A is a bounded linear operator on H. A from H to H, then range of A equals H. Range of A equals H, then we show A star is bounded below. If possible, A star is not bounded below. If A star is not bounded below, suppose A star is not bounded below, what happens here? Not bounded below means there exists a sequence xn presents in H such that this is the bounded below boundedness of A. So since it is not bounded below, we have norm A star of xn. A star is what is A star? That is the adjoint of A. So it is A star of xn, norm A star of xn strictly less than some norm xn by n. Beta norm x, norm x greater than or equals beta norm x. Since it is not bounded of A, then there exists some, suppose A star is not bounded below, then there exists some sequence xn fall in H with a norm A star xn less than some norm xn by n, where n equals 1, 2, 3, etc. Okay. Choose Ya. Choose Ya. Y suffix. Yn equals n xn by norm x. Choose Yn equals n into xn by norm x. So clearly what is norm A star xn? Then norm A star xn. Norm A star xn. Yn equals n into xn by norm xn. Clearly norm Yn. What is norm Yn? Equals n. Okay. And norm A star Yn. Norm A star xn. Norm A star Yn. What is norm A star Yn? Norm A star Yn strictly less than 1. Why? What is norm A star Yn? Norm A star Yn strictly less than norm A star xn strictly less than xn by n. So norm A star Yn strictly less than norm Yn by n. Okay, what is norm Yn? Norm Yn means norm of n into xn by norm xn all by n. So which equals 1. N and n cancelling, so which is equals 1. So that means norm A star Yn strictly less than 1. Okay, so norm A star Yn strictly less than 1. Thus we show that Yn is weak bounded in H. That implies Yn is weak bounded in H. We know weak bounded in H. That is our requirement. Consider Yn fall in H. Sorry, consider Y fall in H. Let Y fall in H. But what is A? A is Ra of A equals H. Range of A equals H means, what is this A? Range of A equals H. A is a bounded linear operator from H to H. Then clearly A is bijective. So Y is in H. A is bijective means A is injective. A is injective. Also A is surjective. A is injective and surjective. Since A is surjective, there exists, that implies there exists some x of all in h such that ax equals y. Because, listen, y is in h, but a, what is a? A is a bounded linear operator from h to h. Since range of a equals h, a is surjective, means there exists x of all in h such that ax equals y. Then, modulus of inner product y and y. Modulus of inner product y and y equals modulus of inner product yn. What is y? Here y equals a of x. This one. Ax. Modulus of inner product yn ax equals modulus of inner product a star yn x. Modulus of inner product a star yn x, which is less than or equals norm a star yn into norm x. But norm a star yn is strictly less than 1, so that implies it is strictly less than norm x. So finally, modulus of inner product y and y. This means modulus of inner product y and y strictly less than norm x. So a subset of a Hilbert space is weak bounded if and only if it is bounded. So clearly yn, modulus of inner product y and y less than x, but y is chosen from h, so that implies yn, here the sequence yn is bounded in h, which is must be bounded in h. Moreover, norm bounded in h and the norm yn goes to 0. Here yn is this one, so norm yn goes to 0. Yes, n goes to infinity. That's a contradiction. This contradiction is due to our wrong assumption. Hence, a star is bounded below. So, when range of a equals h, then a star is bounded below. Okay. Now for the reverse illusion. Suppose a star is bounded below. For reversing, a star is bounded below. When a star is bounded below means norm beta norm x less than or equals norm a star x for all x of all in h with a beta greater than 0. This is our definition. Okay. And now there is a claim. A range of a star is closed in h. Is closed. A range of a star is closed in h. How to prove this one? Range of a star is positive for if a star of xn, if a star xn goes to some y, fall in h. H is a complete space. So when for xn fall in h, suppose a star xn goes to y is in h. Then what about beta norm xn minus xm? Consider this beta norm xn minus x equals beta norm beta xn minus beta xm, so which is less than or equals, by this condition norm it is a star xn minus a star x. Okay, a star xn minus a star x. For n m equals 1, 2, 3, etc. Norm a star xn minus a star xm. Beta norm xn minus beta into norm xn minus norm xm, beta into norm xn minus xm less than or equals norm a star xn minus a star xm. But this means secant xn norm a star xn minus a star xm. That means according to this argument, surely secant xn is a Cauchy sequence. Secant xn is a Cauchy sequence in h. Cauchy sequence in h. If xn goes to x in h, then a star xn goes to a star x. A star xn goes to a star x. Sure. Okay. Then a star xn goes to x in h. A star xn goes to a star x, but a star xn goes to y. That means this y equals a star x. Why? Because of this argument. A star xn goes to y. Y equals a star x. So A star xn converges to some A star x that is y. So this every sequence in A star converges in itself. So the range of A star, that implies range of A star is closed in H. So this is our plane. Let y fall in. Choose y such that if norm A star xn goes to y, but A star is bounded below, then A star is bounded below, then beta norm xn minus xn less than or equals this one. That means secant xn is a Cauchy sequence in H. H is a complete space. So xn converges in H, let it be H. Since H is a Hilbert space, the completeness is preserved. So xn goes to X, xn converges in H. Since xn is a Cauchy in H, but H is a complete space, therefore xn converges in H, let it be X. When xn goes to X, surely A star of xn goes to A star of X, that means range of A star is closed in H. Okay. So, range of A star is closed in H, thus, but range of A star is bounded. Why? Range of A star is bounded, therefore range of A star is a Hilbert space, completeness and bounded. So that means range of A star is a Hilbert space. Okay, A star is bounded. So yes, here A star is bounded. Now range of A star is a Hilbert space. Okay. Let y fall in H. Let y fall in H. Define. Now we define a function. Define g from a range of A star. Define g from a range of A star to k by g of A star w. G of A star w equals inner product wy. Define g from R of A star to k by g of A star w equals inner product wy for all w fall in H. Clearly g is a well-defined function. Now also g is linearity. Why? Because inner product is linear, surely g is linear. Also, mod gz. Mod gz. Let A star is bounded below and injective, G star is a well-defined function, and consider mod gz. Mod gz, let A star w, let A star w equals h. Then gw equals inner product wy, so gz equals inner product wy. So mod gz less than or equals, or mod gz equals modulus of inner product wy, which is less than or equals norm w into norm y. Mod gz less than or equals norm w into norm y. So what is w? And w fall in H, A star w. We have beta norm x less than or equals norm A star. What is A star w? A star w equals H. Okay, A star w equals H. But A star is bounded below. If A star is bounded below, then range of beta norm x less than or equals norm A star x. Okay, yes, beta norm x less than or equals norm A star x. So w fall in H and A star is bounded below means beta norm z less than or equals norm A star z. So this w, which is less than or equals 1 by beta into norm z. 1 by beta into norm z into norm y. Okay, 1 by beta norm z into norm y. Therefore, mod gz less than or equals this one. G is bounded, hence G is continuous. G is continuous on range of A star. G is continuous on range of A star. By Riesz representation theorem on a range of A star, there exists an x fallen range of A star. There exists an x fallen range of A star such that G of Z equals inner product Zx. by arrays representation theorem for set fallen range of A star. Then for all W fallen H, inner product Wy. Inner product Wy equals G of A star H. Sorry, G of A star W. G of A star W equals inner product A star Wx by this argument. G of Z equals inner product Zx. So G of A star W equals inner product A star Wx. Inner product A star Wx equals inner product Wax. Inner product Wax. So here G star AW equals inner product Wy, but G star AW equals inner product Wax. That means inner product Wy equals inner product Wax. So from here, that is Y equals Ax. Y equals Ax. That Ax means it is fallen a range of A. Hence, range of A equals H. Range of A equals H. So when A star is bounded below, range of A equals H. Okay. If you replace A by A star, then range of A star equals H, and A star star is A, then the second result is also immediate. Agreed. So this is our theorem.